போயிட்டாங்களா? சரி, சூப்பர் கேர்ள். எனக்கு வேலை இருக்குது. அம்மா வருவாங்க. ஹலோ, தம்பி ஜாயின் பண்ணிட்டீங்களா? லிங்க் நான் அனுப்பியிருக்கேனே. இது வந்துட்டு இருந்து வரலையா? உன்னோட மெயில செக் பண்ண. அம்மா எல்லாம் கூட Sean Franklin. Sean.
Hello, sir.
Can you able to hear my voice?
Yes, sir.
Okay. What about the screen? Can you able to see my screen?
Yes, sir.
Yeah?
Yes, sir. It's clearly visible.
Okay, Sean, you please inform to other people also.
Yeah,
We'll be
I
having
posted in the group, sir.
Yeah, okay. Totally, how many students are there? 20 or less than 20?
20, sir.
Exactly 20. Okay. How many are from Karunya?
3, sir.
So yourself and Babita, I think. What is her name?
2018 passed out.
2018 passed out. What is her name?
Alicia.
Alisha Mohan.
Oh, I think she is from biotechnology, sir.
She's from biotechnology. One, two, and one more. I think one more girl is from your set, I think.
Ria. Ria is there.
Okay, Ria, yourself, and one more
Blessy.
girl from biotech. The blessing that girl is from biotech. Hmm?
Blessy is from food processing, and Alicia is a passed out 2018 passed out biotechnology.
Yes, only three people are there. Yeah. Hello, students. Good afternoon.
Good afternoon, sir.
Good afternoon. Good afternoon. Yeah, okay, only I think six people have joined so far. The remaining people, I think, since this is the first class, they may have some difficulty in joining the class, I think. Okay, the number 10, Blessy, and Shan Franklin, and Krishna Brinda, Alicia, Gurav Vitali, Joel Matthew, and Sabdar Hasmi. Sabdar Hasmi. Okay. 1, 2, 3, 4, 5, 6, 7 people are there. Okay. So, okay. What shall we do? Only 7 people are there. Okay, so we will do one thing. Okay. Can you one by one can you introduce yourself? Blessy. Can you introduce yourself? Blessy.
Hello, sir.
Yeah. Can you introduce yourself?
Hi, sir. Sir, I'm Blessy from food processing. I'm from Potentiatram. I did my BTech in Karunya.
Now only I was just passed out, isn't it? Okay.
Yes, sir. Yes, sir.
Boss. So BTech you did here only, isn't it? Okay. Okay. Sean Franklin, can you introduce yourself?
Myself, Shan Franklin. I'm from Nail Chris. I did my BTech in Karunya University,
Hmm.
and currently doing my MTech here over here.
Okay. Very good. Very good. Okay. Krishna Brinda, can you introduce yourself?
Good afternoon, sir. I'm Krishna Pranda. I completed my food technology in Kalaslingam Academy of Research and Education, Krishnan Kawal.
Sure.
And
Okay.
presently I
Kalasalingam.
joined MT. Yeah, Kalaslingam, sir.
Okay. I think
Presently I joined.
your seniors are doing MTech here.
Yes, sir. Yes,
Five
sir. Few
students,
of
I
them
think.
are
Five,
here.
five girls are from
Yes, sir.
Kalasalingam, I think.
Yes, sir. 5 girls are from
Five
Kalaslingam.
girls are from Kalasalingam. Okay. Good. Then Alisha, can you introduce
Yes, sir.
yourself?
Hi, sir. I'm
Hello.
Alicia, and I did my BTech in Karunya in
Hmm.
biotechnology, and I worked for 1.5 years in a health tech company as a program
Hmm.
coordinator, and
Sure.
now I joined my MTech here.
Very good. Very good. Okay. Why you choose food processing? Your basic
Uh,
degree is biotechnology. Okay.
yes, sir. Actually, I was interested in food technology. I have to do something, so that's why.
Okay. Very good. Very good. Okay. Then Mitali.
Good afternoon,
Mitali.
sir.
Yeah.
I am Mitali Gurav. I've completed my BTech in food technology, and
Ah,
I am from Chiplun, Maharashtra.
Maharashtra. You are from Maharashtra.
Yes,
How
sir.
to pronounce your name? Gurav Mitali. It has been written Gurav Mitali, but you are telling Mitali Gurav.
Yes, Mitali is my name. Gurav is my surname.
Okay. You are basically food processing, isn't it? Your BTech degree is food processing, isn't it?
Food technology, sir.
Food technology. Okay.
Yes.
Good. Okay. Thank you. Then Joel Matthew. Hello.
Good afternoon, sir.
Good afternoon.
I'm Joel Matthew from Kerala.
Hmm.
I completed my BTech Biotechnology from Sahardaya Engineering College, Thrissur.
What engineering college?
Sahardaya Engineering College.
Sahardia. Yeah. One more
Yeah.
girl. I think your faculty, one of your faculty, she is doing
Yes,
PhD.
ma'am. Yes,
Just
sir.
finished PhD, I think so. She was my
Yeah.
first set BTech student.
Huh.
Not BTech, I think MTech student she was.
Oh, yes, yes.
In 2008 she passed. 2008 or 2009 she passed out being MTech.
Yes, sir.
Previously, I was in biotech department only. I am basically chemical engineer, but
Yes,
my
sir.
first posting was in 2008 in biotech diploma. Biotech
Oh,
department. Okay,
yes.
good, good.
Okay.
Okay.
Thanks, sir.
Then what about the next day? Chella Divya.
Hello, good afternoon, sir.
Good afternoon.
Myself Shaladabya. I'm from Trichy. Completed my BTech in Agricultural Engineering from Kalaslingam Academy of Research and Education, President Royal, sir.
Okay, okay, very good. Very good. You are from Trichy.
Yes, sir.
Okay. The next Jennifer. Thank you. Jennifer 2006. PRK20FP2006. Jennifer. Okay. She may be having some problem, I think. Preeti Jayamangala.
Good afternoon, sir.
Good afternoon.
I'm Preeti. I have completed my BTech Food Technology in Kalasalingam University, and I'm from Madurai, sir.
Okay. Jayamangala. Jayamangala, are you from Karnataka? I think.
No, sir. I'm from Madurai.
Okay. The people, okay. Anne Maria Benny. Anne Maria Benny.
Present, sir.
Yeah, good afternoon.
Good afternoon, sir.
Good afternoon. Tell me about yourself.
My name is Anne-Marie Benny. I have completed my bachelor's in biotechnology engineering from Sahadea College of Engineering and Technology.
Sahadeya
I
College.
come from Kannur.
Ah,
Yes, I come from Kannur,
okay.
Kerala.
Okay. Your basic degree is biotechnology, isn't it?
Biotechnology.
Okay. Okay. Thank you. Okay. Next is Donna Joseph.
Thank you, sir.
Thank you. Donna Joseph.
Good afternoon, sir. My name is Donna Joseph. I have completed my BTech in Biotechnology Engineering from Sahardi Engineering College, Thrissur.
Oh, good,
And I
good.
come from Kavalam, Kerala, Alapura.
Okay. How many people have joined from Sahadeya?
Hello.
Three,
How many?
sir.
Three. Only three people.
Hello.
Yourself, three people have joined. Okay. Good. Good. Okay. Then Jennifer 2006. Jennifer.
Sir, yes, sir.
Yeah.
I'm Jennifer from Chennai, sir. I completed my UG in BTech Agriculture Engineering
Ah.
in Andhra Pradesh, Aditya Engineering College.
Aditya Engineering College. Okay. Nellore. Is it in Nellore? Aditya Engineering
No,
College?
sir. Nearby Rajmundry.
Rajmundry. Sure. Okay. Good. Then Jitesh Rajendra. Jitesh Rajendra. Hello, Jitesh Rajendra is there?
Yes, sir. I
Yes.
am Jitesh Rajendra.
Hmm.
I am from. I completed my UG from MIT College of Food Technology, Pune, and I am native from Jalgaon.
You are native of Kerala. You are native of Kerala?
No, Jalgaon, Maharashtra.
That is Karnataka, northern Karnataka, I think.
No, sir. It will. Sir, it
Okay.
is in Maharashtra.
Maharashtra only. Yeah. Next, Pidadala Sahitya. Hello, Pidadala Sahitya. Hello, hello. Okay. Safdar Hasmi 2005. Safdar Hasmi.
Hello, sir.
Ah, yeah.
Audible?
Yeah, it is audible. Okay.
Myself, Shasta Hashmi. I am from
Hmm.
Nilgiris.
Hmm.
I did my
Oh,
UG in chemical.
Nilgiris. Are you from Nilgiris?
Yes, sir.
Sorry. Okay.
I did my UG in chemical engineering from Periyamaniam University, Tanjavur.
Very good, very good. Your basic degree is a chemical engineering. Very good. I am basically chemical engineer. Okay. Where
Okay.
from? Periyar Maniam, yeah.
Yes, sir.
I think you know about Chitti Babu.
Yes, sir. He is our HOD and is now working in IFPT, sir.
Now he is working in IFPT. Okay, then.
Yes, sir.
Okay, okay. He was in biotechnology department, the Periyar Maniamai biotechnology.
Yes, sir.
I think
Yes, sir.
one
He
more
was my
madam is
FO.
also there. I think her name is I forget. She what is her name? Okay, I forget. One
Okay, sir.
ma'am, she is working there in Periyar Maniamai in biotech department. She is my
Negia, ma'am, sir.
Wow.
Negia.
Yeah, Snegia.
Oh, okay, sir.
Okay. She is the
She was
alumni
from Karunya. She did the MTech in
Yeah.
Karunya.
Okay. She is the first set MTech biotechnology. First set. I taught her.
Oh, sir.
MTech. Okay.
After my UG, I did a job in Ozu, a pharma industry, so actually. For 1.5 years, I was working there for a production supervisor. Then I just resigned and then joined MTech here again for food processing here, sir.
Very good. Okay. It's a good choice for you, I think.
Okay. Thank you, sir.
Okay. You will be able to understand a lot of unit operations. Okay.
Okay,
Then,
sir.
okay. I will tell you about the chemical engineering. What is the role of chemical engineering? Like that, I will tell you. Okay.
Okay, sir. Sure, sir. Thank you. Thank you.
Saraswati Mira. Saraswati Mira.
Good afternoon, sir.
Good afternoon.
Myself Saraswati Meera, and I'm from Tirunelveli.
Tirunelveli. Good.
Yeah. I completed my UG Biotechnology in Shastra University, Tanjavur.
Shastra. Okay, Tanjavur. Okay. Vallam. Is it in Vallam?
Near
Near
Vallam.
to. Okay. Okay. Thank you.
Thank you.
I think 15 people have joined. Totally 20 people are there. 20 students are there. I think I don't know what happened to the rest of the 5 people. Okay, that is not a problem. Okay. See here, most of the people are from biotechnology. Only few people are from food processing. Some are from agriculture background, and only one is from chemical engineering background. Okay. Therefore, see, if you take a food processing, it is a fine blend of food chemistry, microbiology, then food processing and chemical engineering. Okay, everything will be there. Okay, then what I feel, and I am basically chemical engineer. Okay, I did my UG and PG in CIT, Coimbatore Institute of Technology in Coimbatore itself. Then after that, I did my PhD in one of the national university in South Korea. Okay, my area of research is bioenergy and biomaterial, and I produced one PhD, and 2 more people are working under my guidance. PhD, the 2 more people are doing. I was placed in 2018 itself. I joined the Department of Biotechnology in 2018, 8 itself, 2008. Then after that, I got my PhD in Chennai National University, South Korea. I had been there for 4 years. I was in Korea. Then after completing my PhD in 2013, I returned back. Then in 2013, I joined in the Department of Food Processing. Then before 2013, I don't know what is the role of chemical engineering in food processing. Okay. Then I don't have any idea about the food processing in 2000, before 2013. After joining this department, then I came to understand the role of the chemical engineering, and it's like food processing is a very good subject, and a lot of scope is there for food processing. And then after coming to this one only, this department only, I learned a lot. Like even though I am a chemical engineer, I learned a lot about the food processing. Okay, what is its importance? What is the role? And so many things I learned. Okay, it was quite interesting. And okay, currently I am taking all the heat related subjects like thermodynamics, then heat and mass transfer, refrigeration. Okay, these are all my main subjects. I am very much interested in taking the thermodynamics. I am very much interested. Okay. Then apart from this, I am taking the design and the instrumentation, all these things. Okay. For M.Tech, I am taking this refrigeration and the air conditioning. Next semester, I will teach instrumentation paper. It is a very vital paper for you. This instrumentation paper I will teach next semester. Then apart from this, I will be taking this the design paper. Okay. Therefore, these are all the main areas. Okay. Then okay. Then we will enter into the subject. Okay. See here. This is the refrigeration, and all of you can able to see my screen. Hello.
Yes, sir.
Can you able to see my
Yes.
screen? Okay, definitely.
Yes, sir.
Okay, therefore the thermodynamics is the base for refrigeration. Thermodynamics. Okay, therefore, if you take a chemical engineering, there is a 8 pillars of chemical. We call it as pillars of chemical engineering. Okay, that is the thermodynamics, process calculation. You read the process calculation under the title, principles of a process, principles of food engineering, like that. You will be reading, I think. Okay, that is the calculation. Okay, if you want to produce some food, it may be a biryani for 100 people. Okay, how much rice we have to use, how much vegetable you have to use, how much water we have to cook, we have to use, how long we have to cook, like this. Okay, therefore that is the material and energy balance. Material and energy balance. The main topics under process calculation is the material and energy balance. Of course, this BTech biotechnology students also, they read about this material and energy balance. Okay, chemical engineering, it is a main chemical engineering subject only. And I don't know about the this agriculture engineering students. Okay, I don't know whether they studied about the process calculation. I'm not sure. Then next comes the thermodynamics. Thermodynamics is a very vital subject. Okay, in thermodynamics, what we are going to study, if you take any reaction, whether the reaction is feasible or not, the feasibility of any, not only the reaction, any process, the feasibility of the process. Okay, we will be studying about the feasibility of the process. Okay, and there are different laws of thermodynamics are there. First law, second law, zeroth law, and the third law. Okay, so anyway, we are going to see in detail. Okay, therefore, this is the second pillar of the thermodynamics. Okay, that's a very vital subject. Okay, then the thermodynamics is applicable for all the system. It may be a mechanical system, it may be an electrical system, or it may be a biological system. Okay, any system, this thermodynamics is applicable. For biotech students, I think they studied about the biothermodynamics. There is a topic called biothermodynamics. Okay, they used to read thermodynamics. Okay, therefore in that they will be studying about the what is that, the respiratory quotient, and what is that, oxygen transfer. So many topics. Okay, they will be studying under biothermodynamics. Okay, then the next comes the unit operations. Okay, unit operations. Okay, I think in Karunya they are studying operation one and the unit operation. Unit operation. All of you, please mute your mic. All of you, please mute your mic. Okay, please mute your mic. Okay, somebody I think unmuted their mic. Jennifer, can you mute your mic? Jennifer 2006. Okay, therefore this is the okay. This is the second pillars of thermodynamics, second pillars of the chemical engineering. Next comes the unit operation. The unit operation, okay, unit operation we can divide into two. Some unit operations are the separation process. You will be provided with a mixture, and your objective is to have to separate the mixture into its individual component. That is called unit operation. In some cases, you will be provided with the individual components, and you have to mix the component, and you have to get a homogeneous mixture. You have to get. Okay, therefore that also comes under unit operation only. In the unit operation, there won't be any chemical reaction. No chemical reaction is involved. Okay, if a chemical reaction is involved, that is called a unit of process. Example for the chemical reactions are isomerization, reduction, oxidation, then hydrogenation, dehydrogenation, something. Okay, therefore these are all the chemical reactions. The process which involve the chemical reaction, we call it as a unit process. Okay. Then even enzymatic reactions, that also comes under the unit process only. Then for the case of unit operation, there won't be any chemical reaction, only the pure physical properties. Okay, by using the physical properties, either we have to form a mixture or we have to separate the mixture into its individual components. That is the unit operation. Okay. And next comes the heat transfer. Heat transfer is a very fundamental thing. That is, it is needed for the thermal process. You can divide any food processing into thermal and non-thermal processes. Okay. In those days, thermal process played a vital role. Now also, people are practicing the thermal process, but even then, apart from thermal process, a lot of non-thermal processes are there. Non-thermal process. Okay, non-thermal processes like sonegation, then not ohmic heating, then ultrasound, then some other techniques are used for reducing the microbial load and to enhance the shelf life. Okay, this is the unit heat transfer. Okay. Then next comes the design paper. Okay, the design, it involves everything. Okay, it needs the knowledge from various aspects of chemical engineering. Various aspects, I mean, it needs the knowledge from thermodynamics, needs knowledge from heat transfer, mass transfer, unit operations, process calculation, everything. Okay, after reading all these things only, you can do any design. Okay, that's why the design has been kept in the seventh semester, or in maybe in the sixth or seventh semester. It will be kept normally, because it needs knowledge from different branches of or different topics. Okay. Then we will come to the refrigeration. Okay, refrigeration. Our object, refrigeration means producing low temperature. Okay, our refrigeration means producing low temperature. Our objective is not only to produce the low temperature, but we have to maintain the low temperature. That is our objective. Okay. Therefore, if you see the base of this refrigeration, the base is having a thermodynamics. Okay. Just what in this class, what we are going to do, just we want to recall whatever we studied in the thermodynamics, in the UG, whatever we studied thermodynamics in UG. Okay. Then, of course, these are the thermodynamics. Okay. The thermodynamics is based on law of conservation of energy. Law of conservation of energy. Especially the first law of thermodynamics is based on law of conservation of energy. The law of conservation. Law of conservation of energy, law of conservation of mass, and law of conservation of momentum. Okay, three laws of conservation are there. Okay. The law of conservation of energy states that energy cannot be created and cannot be destroyed also. The thing is, one form of energy can be converted into another form of the energy. The total energy of the universe remains constant. The total energy of the entire universe it remains constant only. It is not the thing is, one form is converted into another form. Okay, that is happening continuously. Okay, without any break, one form is converted into another form. That's all. Okay, that is the law of conservation of energy. Okay, the next we know of course they have given two different types of the approaches. One is the macroscopic approach, another one is the microscopic approach. Okay, the microscopic approach is called statistical thermodynamics. It's called statistical thermodynamics. Microscopic approach means in the molecular level what is happening we have to see. Molecular level. I think BTech food processing students, they studied even the chemical engine, they studied thermodynamics a lot. Chemical engineering students, we will be having two thermodynamics, thermodynamics 1 and thermodynamics 2. Okay, in the statistical thermodynamics deals with the at molecular level what happens. That is, we studied about the fugacity, activity coefficient, then Gibbs free energy, chemical potential. All these things are at the molecular level. Okay, macroscopic thermodynamics. I think there's a mechanical people, they will study about the macroscopic approach. Mechanical people, they will study about the macroscopic approach. That is, what will happen, how to get the maximum from a turbine, from maybe a nozzle, from other big equipments. Okay, how to get the maximum out of that one. Okay, that is called the macroscopic approach. Okay, the next comes the continuum at this stage it is not needed. Then the thermodynamic systems terms we will see. Okay, the first one is the thermodynamic system. System means the physical world where we are going to concentrate our attention. Okay, where we are going to concentrate. That is called the part of the physical world where we are going to focus. Okay, that is called the system. That's all. Surrounding means apart from the system, whatever present, that is called the surrounding. And boundary means the boundary may be a real one or it may be an imaginary one, the which separate the system from the surrounding, that is called a boundary. Okay. For sometimes what will happen, we may have a real boundary. That means the boundary we can see, we can sense. In some cases we know we cannot see. Okay, that is called the imaginary boundary. Okay, we will see later. I will tell you what is an imaginary boundary and all. Okay, therefore this is called a boundary. And if you take a boundary, then again the types of the boundary they have given. Okay, the first one is made up of rigid wall or fixer. Okay, here some amount of gas has been kept in the cylinder. Okay, the walls of the cylinder, I can call it as a boundary. That too I can visualize, isn't it? Okay, the second thing, this boundary is a fixed boundary. This boundary is a fixed boundary. Okay, and a movable boundary means that the boundary can move, especially if you see the piston. The piston can move up and down based on the pressure inside the cylinder, wasn't it? Okay, therefore it is a movable boundary. Okay, the second thing is impermeable wall. Impermeable wall means the wall will not allow the mass to pass through. Okay, that means see this the wall which is made up of this boundary, this piston and as well as the cylinder. That is an example for the impermeable wall. Okay, now for impermeable wall there is no exchange of mass with the surroundings. But for the case of a permeable wall, it can exchange both the mass and as well as energy with the surrounding. If mass goes out of the system, then what will happen? The mass will carry some amount of energy with it, isn't it? Okay, therefore the energy also will escape along with the mass. Okay, the next is adiabatic wall. Adiabatic wall means there is no exchange of heat with the surrounding. Otherwise we can call it as an isolated. It is called an isolated solvent. Okay, diathermic wall means the metal wall is an example for the diathermic wall. It can exchange energy with the surrounding but not the mass. Okay, these are the different types of the boundaries. The next system, open system, closed system, and isolated system. So for example, open system, they have given a nozzle. They have taken a nozzle. Okay, we can take anything. Even if you try to boil. See, I have taken some amount of liquid in a beaker. I am trying to boil this liquid. Then what will happen? It is a open only. Okay, the beaker is kept open only. There is no lid on the top. Okay, what will happen? The molecule will escape. Okay, if you heat, then what will happen? The liquid will be converted into vapor. All the vapor will be exchanged with the surrounding. Okay, therefore it is an example for the open system. Or we can say in the open system, the system can exchange both mass and as well as energy with the surrounding. Okay, that is an example. Okay, here we have taken the nozzle lesson. Okay, see here, this is this is our system. Only this area is our system. Therefore, here here the fluid is coming in, and here the velocity. If you see the velocity here and here, if you compare the velocity V1 and V2, V1 will be less than the V2 because the cross section at the exit, that is very small. Therefore, the velocity at the exit of the nozzle will be the highest. Okay, compared with that at the inlet, isn't it? Okay, here I have taken a very small area, and this is taken as the system now. Here, whatever the material which comes in, that will undergo something inside the nozzles and some change. And after that, all the material will go out of the system. Therefore, it is an example for the open system. Okay. Next comes the closed system. Okay, closed system, the same heating, what I can do, I can heat the content of the beaker just by closing the beaker. Okay, if I close the beaker content and if I heat, then what will happen? The inside the pressure may increase, but the molecules cannot go out. The molecules cannot go out. Doesn't work. Okay, so then such system are called a closed system. then what will happen to the heat energy? The heat energy will be dissipated through the wall. The heat energy will be dissipated through the wall, but the material cannot escape from the beaker. Isn't okay? Therefore, the mass cannot go out, but the energy can go out. Isn't okay? Therefore, this is an example for the closed system. And for the isolated system, for the isolated, it is made up of some insulated wall. Example for the isolated system is the thermos flask. Okay, either it is a double wall. So okay, therefore if you place some content into the thermos flask and you tightly close, and what will happen? No material can go out. One thing, because I tightly closed. Okay, the second one, the heat and also cannot escape. But the thing is, if it is so, then such type of system is called the isolated system. But perfectly isolated system, to design a perfectly isolated system, that is very difficult. Very difficult. Okay, three modes of heat transfer. What are the three modes of heat transfer? Convection, conduction, and radiation. These are the three modes of heat transfer. Isn't it? Okay. And what will happen to the if you take a thermos flask, since there is no material is escaping, the conduction and the convection is absent. But what about the radiation? Radiation may be there. Because of that radiation, only what will happen after 12 hours or maybe after 18 hours. If you see the content inside the thermos flask, the temperature will be slightly down, or it may reach the room temperature also, because the content will lose its energy by means of radiation. Therefore, a perfectly isolated system is very difficult to design. Okay, but near to isolated system, that we can try to design. Okay, therefore these are the three types of the system here. And if you take your open system, here there is an exchange of energy and as well as mass. Therefore, we cannot say the change. Okay, the mathematical expression we have given. Okay, see here they have given the mathematical expression here. What is the mathematical expression for the open system? dE is equal to 0. dE means what? Change in energy. Change in energy is not equal to 0. Means what? There is a change in energy. There is a change in energy. The meaning is dE is not equal to 0 means change in energy is not equal to 0. That means there is a change in energy. Okay. Similarly, dm, m is nothing but the mass. Okay, there is a change in mass. There is a change in mass and change in energy because the system is open now. Okay, and here there is a change in my energy, but there is no change in mass. Why? For the case of a closed system, because it is a closed system, I am not allowing the mass to escape. Okay, therefore the dm is equal to 0. Change in mass equal to 0. There is no change in mass. The meaning is okay. But if you take an isolated system, there is a no change in the energy, no change in the mass. Okay, this is I am talking only for the ideal system, ideal isolated system. For the non-ideal isolated system, the dm may be 0. There is no change in the mass. But what about the energy? The energy will be slowly will escape from the system. And after maybe after some time, if you see, there won't be any, or it will be in equilibrium with the surrounding. Okay, these are the three different types of the systems here. Then next comes a okay. I'll have to wait for 2 seconds. Sorry. Control volume means sometimes what we can do. Okay, if you take any system, the system means what? First system means the part of the physical world where we are going to concentrate. Okay, that part we are going to call it as a system, isn't it? Okay, sometimes the system will be well defined and the boundaries of the system also we know, we can visualize. In some cases, the boundary of the system we cannot visualize. If it is so, what we can do, we can take a control volume. Okay, say assume that the fluid is flowing through different stages. If it is so, the first stage of the fluid I can take is the control volume. Just I am going to concentrate to what is happening in the first stage alone. If it is so, then that part of the system is called a control volume. It's called control volume. Okay. And then of course these are all very simple only. Okay. Then the next comes the thermodynamic variables. Okay. Variables. Okay. Why variables is needed? Okay. Say if I take a carbon dioxide CH4, I have taken CH4. Okay. I'm telling that CH4 in a cylinder. If I tell. Okay. In that case, we can say the system is not well defined. Okay. I have taken a cylinder. In the cylinder, methane is there. I am telling that CH4 in the cylinder. If you tell like this, then it means the system is not well defined. We have to tell at what temperature, at what volume, and what pressure, how much quantity, okay. We have to tell everything. Okay. If you tell everything about the CH4, about the methane, then we can say the system is well defined. I have taken 10 mole of CH4 at a temperature of maybe 70 degrees, at a volume of 5,000 liters, at a pressure of 2 atmosphere. Okay, if you tell like this, then we can say the system is well defined. It is well defined. Okay. Therefore, the state of the system can be expressed with the help of properties. The state of the system. The state, I mean the properties. The properties like you see here, temperature, volume, pressure, number of moles, like that. Okay. Therefore, this is called the properties. Okay. Not only these properties, I have n number of properties are there. Like this is okay. This is the H is the internal enthalpy. Capital H is enthalpy. This capital U, capital E is the internal energy. This is the entropy. This is the work done. This is amount of heat. The number of moles, pressure, volume, temperature. So many things are there. Okay, with the help of so many properties, I can state when the system is in what state. The system is in what state. Therefore, the property is needed. Therefore, we have to understand what is that property. Okay, if you take the property, the property can be divided into two. One is the state variables and the other one is the path variables. State or state properties and other one is the path of properties. Okay, then no, before going to the that is the process. Okay, before going to the variables, there are two types of variables are there. One is the intensive variable, and other one is the extensive variable. Extensive. Okay, what do you mean by intensive? Intensive means if any variable depends upon only the mass and volume. If a variable depends on mass and volume, then that variable is called intensive variable. If the variable is independent of mass or volume, then we can say that variable is the extensive variable. That variable is called extensive variable. They have seen so many variables. See here temperature, volume, pressure, number of mole, enthalpy, then internal energy, entropy, work, and on the what is that Q. Okay, these two are not variable. Then this called as we can call it as a variable, but these are the variables in transit. During the transit only we can express these one variables. Okay, rest of the variables you can take temperature, volume, pressure, number of moles, enthalpy, internal energy, and entropy we can take. Okay, if you take these variables can be divided into intensive and extensive variables. We can broadly classify. Okay, I will take the temperature and temperature and maybe the enthalpy also I will take. Okay, temperature and enthalpy, two different variables I will take. Okay, we will see what are the difference between these two variables. Two different variables. Okay, first I am going to take the temperature, and second I am going to take the enthalpy. I am going to take. Okay, first we will see here. All of you listen here. See, I have taken 100 ml of water. I have taken 100 ml of water. I have taken. Okay, it is at a temperature of maybe 25 degrees. The water is at a temperature of 25 degrees. Okay. Now what I am going to do, I am going to split into two different volumes. That is this. I am going to split. That's all. 50 ml, 50 ml each, 50 and 50 ml each. I am going to split. Okay. Therefore, now I am going to check what is the temperature after splitting. I'm not doing anything. Just I have taken 100 ml of water in a beaker, and I am going to check what is the temperature. The temperature is 25 degrees. Then after that, I split into two. There is a 250 ml. Okay, and I am going to check what is the temperature here, and then here I am going to check what is the temperature. Just after splitting, what would be the temperature? The temperature will be the same. The temperature will be the 25 degrees and 25 degrees, isn't it? 25 degrees, isn't it? Okay. Therefore, before and after splitting, the temperature is same only, isn't it? Okay. Therefore, or I can say the temperature is independent of the volume, isn't it? Temperature is the independent of the volume, isn't it? Okay. Here V total is equal to V1 plus V2. I can write. Okay. Therefore, the temperature is independent of the volume. Whether I have taken a small quantity from the system or I have taken the entire quantity, the temperature is not going to change with respect to the volume or mass of the system. Okay. Therefore, temperature is also one of the variable here, isn't it? Okay. Therefore, the temperature, which is one of the variable, is independent of the volume. Therefore, that temperature I am going to call it as intensive property. It is an intensive property. Okay. The property which is independent of a temperature, which is independent of mass or volume, is called the property which is independent of a volume or mass is called intensive property. Intensive property. Here the temperature is the intensive property. Good. Okay. The next comes the enthalpy. What do you mean by enthalpy? The total heat content of the system is called enthalpy. The total heat content. Okay. Therefore, see, I have divided the system into two. One is the 50 ml, another one is also 50 ml. And what will happen to the total heat content of these? Definitely, I can write like this. What I can write? Total heat content of the system is equal to H1 plus H2. I can write. So total heat content, assume that it is a calorific value. If you take the calorific value of 100 ml, or the energy obtained from 100 ml of water and 50 ml of, maybe 100 ml of petrol and 52. Okay. See here, 100 ml of petrol I have taken. 100 ml of petrol I have taken. Okay. Then that I split into 250 ml of petrol. Good. Okay. If I burn 100 ml of petrol, the energy which I can receive from 100 and by burning 100 ml of petrol, that will be equal to the sum of the 50 ml of petrol I burn. Okay. Therefore, energy obtained from burning 100 ml will be equal to energy obtained by burning 50 ml of petrol. Again, 50 ml of petrol I can write, isn't it? Therefore, the total heat content or total energy, it depends on what? Volume, isn't it? The total heat content or total enthalpy, that depends upon the mass or the volume, isn't it? Okay. Therefore, the internal energy and the enthalpy are the extensive property. They are called a extensive property. They are called extensive property. All of you can able to understand? Okay. Otherwise I can write the intensive property will not have additive nature. Additive nature means what? I cannot add. Say here, wait. If you take an intensive property temperature, the temperature of the temperature of the 100 ml is equal to temperature of the 50 ml plus temperature of the 50 ml. I cannot write 50 ml. I cannot write, isn't it? Okay. Therefore, it is not having additive. Additive means addition. It is not having additive property, isn't it? Okay. Therefore, the temperature is an intensive property. It is an intensive property. But if you take energy, if you take energy, E of the total is equal to, or E of the 100 ml is equal to E of the 50 ml plus E after 50 ml I can write. 50 ml I can write, isn't it? Okay. It is having additive nature. Which one? The energy. Therefore, the energy is an extensive property. Extensive property. Okay. All of you can be able to understand. Okay. Therefore, the property which cannot have the additive nature is called intensive property. The first one is not having additive property. Okay, and second one, E is the property is having additive nature. Therefore, it is an example for the extensive property. All of you can understand. Okay, this I can easily remember how intensive, independent, intensive, independent. You remember like this: intensive, intensive, independent. Intensive, independent of mass. Extensive depends on mass. Extensive depends on mass. Depends on mass. Extensive depends on mass. Okay. Therefore, independent intensive property means independent of mass or volume. Extensive means depends on mass or volume. They are called the extensive property. This is intensive property. These two you have to understand. Okay. Therefore, the see here. Okay. Oh, all of you. I think it is not. It is now the time. It is. All of you. It is time. It is 2:51. Okay. So all of you can able to understand. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. It's all these things are very basic one, very simple. Okay. Yeah. Have any doubt? Okay. Okay. All these things are very very simple only. You don't worry about all these things. Okay. And second thing, these are all the basics only. Just we are recalling all the basics. Okay. That's all. Okay. But anyway, this is not going to be asked in your internals. Okay, just I want to revise all these things. Okay, then after that we are going to study what are the first law, second law, third law, and zeroth law of thermodynamics. The refrigeration is based on second law of thermodynamics. Refrigeration is based on second law of thermodynamics. Refrigeration will be quite interesting. Okay, refrigeration, air conditioning, it will be quite interesting. Okay, it plays vital role in food processing. Okay, okay. All of you can leave. Okay, when is our next class? I think day after tomorrow we will have the next class, isn't it? Sean Franklin, when is my next class?
Yes, sir. It's on Wednesday.
Tomorrow, I think by 10 o'clock, isn't it? Day after tomorrow.
Like
okay, Wednesday by 10 o'clock we have the next class. Okay, we will see in the next class. Okay, okay. See you. Thank you.
Thank you, sir.
Sir, attendance, sir.